C. So I think clear is CL, in this case CL7, and it has deleted the breakpoint. So you can always say help clear, oops, clar. So it explains what it does. Okay. Any questions? Yep.
I noticed it said that you were deleting breakpoint 2 there. So is the numbering from when the program starts to when the program ends?
It's 2 because I have used and deleted the first breakpoint. It does not reuse the numbers.
Okay.
So you just pick the next available number for the next breakpoint and so on. Until I'm not sure when it wraps around maybe 16-bit. Yep.
Is there a way to save breakpoints between sessions?
Not natively. What you can do is you can probably use a command to list all the breakpoints and have that to redirect that to a file. And that may do it. So you might want to do a help breakpoints and then find out how you can list all the breakpoints that you have set so far. And none of these. Disable, enable, ignore, save. There we go. So when you type, so when you type help save, it explains, when you say save breakpoints, it will save current breakpoints definitions as a script. So that implies that you have to use it along with a, let's see, save breakpoints. So I need to supply a file name. So when you get back into GDB the next time, you can run that particular script and it will set up the same breakpoints again. Good question, very good question. Okay, any other questions? No other questions? Why do we have to do this? I mean, isn't a GUI a whole lot better than having to do all this stuff, by typing and a text interface?
Not really.
Not really, because once you understand, how to set the breakpoints, how to continue execution and stuff like that, you can write your own script to GDB, so that you can use GDB to quote-unquote automatically test your programs the way you want your program to be tested. Okay, now that's a very nice feature because now you don't have to say, oh, I'm not sure I have tested all the conditions, because you can type all the conditions, all the test conditions, all the breakpoints where you have to stop, and all the variables or registers that you have to check. You can input all of that stuff into your own script. And then when you're in GDB, all you have to do is to say, okay, run this script here, do all these commands automatically. Okay? The scripting language also supports loops. It supports conditional statements. It's basically a scripting language all on its own. So you can automate a lot of stuff when you understand how to write your own script in GDB.
So now we need a debugger for our scripts too.
Yes. Well, that's how I grade homework assignments for a class like this. I mean, this class has 46 and soon to be 47 students. Okay, it's going to take me a lot of time to test each program manually, by hand. So I rely on the script to help me in that process. Any questions about GDB at this point? No questions? Okay. So to get out of GDB, there are several ways to get out. You can say quit. You can also use Control-D to get out, because when you type Control-D, you are telling GDB itself and say, okay, we are at the end of the input to GDB, and GDB recognizes that and say, okay, it's time to get out of the debugger itself. Are there any questions about using GDB in general? No questions? Okay. Now remember, this is all being recorded right now, so that means if anyone wants to replay what I just did in GDB, you can actually go to YouTube, find today's lecture on video clips, and just replay that portion of the video clip. It comes in handy sometimes. Saves me all the trouble when someone asks me, could you say again how to do something? No, watch the video clip. Okay. So So this is just a repeat, or explanation of, all the commands. You can probably read it on your own. There's nothing really too, interesting or too difficult to understand. We are not going to talk about accounts because we don't have accounts on Power anymore. So we can skip all this part here. And let's see, can I go back to here? Yep. So now I'm switching back to the Moodle screen because we are basically done with Linux commands. That part is done. Okay. So the next part is to answer one of the questions that many of you probably have, when you enroll or try to sign up for this class. Why do I have to learn how to program in assembly language?
Because we were told to.
Because it's a prerequisite.
It was on my sheet.
The degree requires it, right? That's why I have to take assembly language programming. Well, let's go ahead and take a look at how assembly programming language fit in the big picture. So the first part basically just talks about something that you already know. Okay, when I use the abbreviation HLPL, that stands for High Level Programming Language, and a typical example of that is C and C++. Okay, it's a high-level programming language. And we can find other examples too, Java, PHP, Perl, Python, and so on and so forth. Okay, they're all considered high-level programming languages. And that's because these languages, they all have constructs that closely, in double quotes, resemble logic concepts that people use. So I'm talking about conditional statements. If this condition, then perform this statement. And if, okay, that's something that people natively understand, or it's actually easy for people to understand. You can say repeat a block of code until a condition, and that's relatively easy for people to understand as well. That's why these are called high-level constructs, because they map to how we usually think. A program source file of most high-level programming languages is merely a text file. Since you have all taken cisp310 and possibly cisp400, you already know that part. If you want to write a program, you can use Notepad. If there's no tool available, use Notepad. And I can write a program using cat. Right? I just did earlier in the class. Okay, when I pasted that code using cat, I could have typed it by hand. Okay? In other words, it's not easy, it's not difficult to create the source file in a high-level programming language. Unfortunately, this source file, which is just a text file, is meaningless, completely meaningless to the central processing unit, the CPU of a computer. Okay? So something has to happen before I can actually run programs written in C, C++, Java, PHP, and so on and so forth. In this class, we'll focus on compiled languages, so that way we are restricting to C and C++ for the most part, because Java is compiled, but it is compiled to a virtual machine language. PHP is interpreted, Perl is interpreted, Python can be compiled, Visual Basic is sort of compiled like Java, and so on. So we'll focus on C and C++. So we look at the processor, okay, the other end of the spectrum. On one side, we have the programmer who likes to use high-level programming concepts, variables, types, if-then-else statements, conditional statements, subroutines, return values, arguments, and so on and so forth. Those are all high-level constructs. The processor doesn't care about those things. The processor is going to ask memory for a binary bit pattern every single time. So usually it is with a 32-bit processor. Each binary pattern has 32 bits. Okay, it will look at the 32 bits and say, "Oh, this is 11010100011010. Oh, it means add. Okay, I can do add." Okay, it executes the add instruction. It will usually add, two registers, a value to a register, and so on. We'll talk about the add instruction later. Then it will go fetch the next available instruction, which is another binary code. Look at that code, go like, "Oh, I can know how to do that. I can copy, register A to register B," and so on and so forth. That's how the processor works. Okay. And those instructions are not really easy for people to remember. Okay? If anyone is interested in those instructions, let me see. I think there's a disassemble option with object dump. So let me find out how to do that. Disassemble -D. Okay.
Too small.
Oh, that's the small one, huh? Go for the big one.
Thanks.
Okay. Object dump -D test.out. This is the program, and it shows you both the assembly language version and also the machine code version. This is the assembly language version, push AX. Now I know we haven't talked about push AX, and it's kind of cryptic already, but we kind of know that it has something to do with a stack. Okay, for those of you who have taken data structure, push is an operation related to a stack. So we kind of have an idea that we are trying to save a register and to restore a register or something like that. It has some meaning. It has something that looks like English words. Okay, let's put it that way. The other side is 66 as a hexadecimal number, 50 as a hexadecimal number. In other words, this is already easier for us to understand, because as far as the processor is concerned, what do you think it is seeing? It is seeing 1010, 0101, 0000. Yes, I can translate from hexadecimal to binary that fast. And you will too. Not to scare people away from this class. Okay, the next one. Okay, this is a 16-bit pattern. The next 16-bit pattern is, once again, 1010. No, is it? No, 0110, 0110. I was wrong in the first one too. And then we have 0101, 1000. Okay, that's a 16-bit pattern to mean pop AX. Okay, so do you want to program using this, or do you want to program using this?
I like the right hand.
Neither, but if you have to choose one, right? So if you have to choose one, the one on the right hand side is still a little bit better than the one on the left hand side. Okay, so the next question, which is irrelevant to this class, who in their lost mind is going to program using machine code, using all zeros and ones, not even hexadecimal numbers? Well, I have to.
Very old people.
Would that be you?
Or a really, really old machine. Let me show you the Altair. Altair computer, probably. And I want to show you a picture. I mean, the picture is, what I really want. Do you see a keyboard here? No. Do you see? Well, no keyboard is okay as long as there's Bluetooth or USB, right? I don't see any Bluetooth or USB here. I do see a lot of switches. So with a computer like this, how do you put a program into the computer? Pop in a CD, right? There's no CD tray either. Okay? So the way you do it is you flip these switches. Okay? One bank of the switches is probably responsible for the address. Okay? So you flip a whole bunch of switches, you specify, okay, now we are talking about this address here. Okay, 011010. Okay, that's the location where you want to store. What are you going to store? Oh, remember the other picture? The dump from the executable, 6650. Okay, let's say you want to store that 16-bit pattern into that location. Well, I can't do it here because it doesn't have enough switches, because you will need 16 switches in that case. Okay, so with the 16 switches, you will have down, up, down, down, up, down, down, up, down, up, down, 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 down. That's the first 16-bit pattern. And then there's another switch here, which is a toggle switch. Okay, it's a momentary switch.